Yeah, so our next session will be by Professor Dheeraj Garg of Shiv Nadar University. So, just a second. Yes, I can see that your presentation is already there. So, Professor Dheeraj is a professor in the Department of Chemical Engineering, School of Engineering, Shiv Nadar University. So, sir, over to you. You can start your session.
Okay, thanks a lot. Good afternoon, namaskar everyone. So welcome everyone to this workshop, and we are taking few courses, a few sessions on meshing. So Professor Hari Krishna sir has already taken one session on introduction about meshing, the purpose, what are different types, and so on. And you also had some hands-on on meshing in the previous sessions. I would like just to add more information, more understanding of what exactly meshing is and how it is going inside the open form. So in this, I will discuss about the mesh specification and the validity constraints, how the numbering is done with the vertex, face, and edge, how the mesh is generated, and in the end, why do we require so many different types of meshing? So each of the thing is important since you are doing on the open form where you have to write certain code. So you should have a visualization of what is happening inside and why it is required. So the major source of content here, I have taken it from OpenFOAM itself. So for details, you can actually go to this link and actually go through it for more details. So let's start with the classes. So the first is how to specify mesh and what are the constraints to validate it. So the basic thing is mesh to start with the point, which is zero dimension. Okay. So we need to have points and they are located in 3D space. And what we do in open form is that we create a list and the numbering of each point starts from zero. Okay. Unlike in other case, we say one, two, three, it starts from zero. So if we have 3 points, it will be numbered as 0, 1, and 2. Okay. Now there are things that you cannot have two different points. The base of the mesh is the points, which are zero dimension. They are located in space and they are numbered from zero and they are stored in the with the numbering. Now the thing is that you cannot have two different points with two different number but exactly the same identical location, same identical position. So there can only be one point with the same identical position. Besides, another the constraint is that there cannot be any point that is not part of at least one phase. Okay, so that means each point must be connected and it must be part of the phase. There cannot be isolated points which are there. So sometimes what happens, we may create many points, but we forget to connect them, and that will may cause any issue. Give you warning that there is a issue. Then from these points, we want to generate faces, which is basically two dimension. So we cannot jump from 1D, 0D to 2D. So what you need is how to generate faces. It's basically done using the ordered list of points. So ordered list point means the point may have its own numbering, but you need to tell in which order you need to put so as to create face. Now, what is the importance of order is that when you connect two neighboring points to in the list, it creates edge. Edge is one dimensional structure, just like a line segment. Okay. So once you are connecting edges, when the edges are connecting back to origin, it completes the thing and face is created. And once face is created, it's like a plane, and every plane is having a direction which is represented by a normal vector. And as it's a direction normal vector, we use the right hand rule. And you can remember that like A4 sheet is there. So you can write on both sides. So just to visualization, you can say one side is blue and another is red. So blue is in the positive direction or which is the preferred direction, and the opposite direction or negative, whichever you want to as a reference, is the red one. So blue we are talking is in the positive direction. So we can see this here, like this is the face created from points. So point 0 going from 1 to 2, 3, 4. This is how you write it in OpenFOAM, and it creates a face. Now remember this thing, instead of writing like this, let's say I change the order. Instead I write the order, let's say 0, 3, 2, 1, and then 4. So do you think, despite mentioning all the 5 points, will it create any real face? The answer is no, because it will change the formation of edges. From 0, it will go to 3, 3 to 2, 2 to 1, and 1 to 4, and 4 to 0. So these two additional edges and the sequence will not create a realistic face or a surface. So order is important. Another thing is that in the same 5 points, depending on your mentioning, like 0, 1, and 2. Let's say I stop at this point itself. Then what will happen? It will create a face from 0, 1, 2, and 2, 0. So this can be one different face. I can create another face 0, 2, 3, and 0. So like this, I can create a face by minimum 3 points. I can use more points, but minimum 3 points are required to create any face. And remember from the geometry, 3 points are always coplanar. Only when 4, 5th are there, they may or may not be in the same plane, which will add additional complexity. Now, moving to further things of the complexity of faces, then there are two different category of faces we see in the meshing. What is called internal faces. What is meant by that is that in internal faces is between the cells. So when you are creating several cells, the common face between both of them is the internal face. Now it has to become part of both the face. Okay, and since this is common, so the face normal point into the cell with a larger label. So larger label means the cell which is the direction of normal on the surface would be from the cell which is formed first towards the cell which is formed later. Okay, so this is how we are doing. And from the previous case, when we are talking about faces and the direction, we always follow right hand rule. So all the faces that should be made should have the normal towards the positive coordinate direction we have chosen, so as to have the consistency. Okay, so now these are the internal faces. Now another type is the boundary face. So internal face will always see two faces on two cells on both sides. It will be a common surface, whereas the boundary faces are the one which will have only one cell on one side, but other side there will be no cell of the same block. There may be another block, but it's not part of the same block, and hence it has to act as a boundary. Okay, so it will coincide with the boundary of the domain and addressed by one cell only as a boundary patch. And the face points, so that they are normal. If you look at the normal, they will point outside the computational domain. So when it is pointing outside the domain, it will not encounter any cell within the computational domain. Now from this we want to generate. So we have come from 0D point, we have come to the edge 1D, and from edge we generate 2D faces. Now together we create this cell, which is 3D structure. So here they can be list of faces in arbitrary order. No particular order is necessary, but there needs to be certain important things, properties, so as to ensure proper cell. And what are those? So first is the contiguous. That means they must, when you are creating cell, it must completely cover the computational domain, first thing. That means no portion of the domain should left without any cell. And second, they must not overlap one another. That means they must share the faces, but not the face should not be present in some of the cell inside the cell. It must be at the surface. Otherwise, this will not be realistic for normal meshing. Second thing is the convex. Now, what is the meaning? Well, we simply say cell centered inside the cell, but the convex meaning is coming from geometry. A basic definition says if you take any two random points in a given structure. So let's say there is a plane given of any given boundary. You take any two random points, including boundary, and you create a straight line between the 2 points, At no point this line will go outside the plane, outside the structure. So such structures are called convex. If it is going outside at even a single point, then that geometry is not convex. Okay, so this is to ensure that all points are in a way that every point connecting line between them is within the system cell itself. Then another point property should be closed. Then the cell must be closed. And what does it mean? There are two parts. One is called geometrical close. So all face vectors, area vectors are oriented to point outward of the cell. So their sum should equal to 0 vectors. So if you have created the faces consistently in the positive direction, so if you look at the cube, let's say you create a cube in x direction. So looking from outside, one direction in the beginning, one side would be red and another side would be blue. So when you add both of them, one is positive, another is negative, the area sum will be 0. If both are blue, then it will be an unrealistic thing. That's why you need to create in a uniform way. Second is the topological. This was the geometrical. That means the direction of faces should be in the same proper way. Second is the topological. Topological dictates that all the edges in the cell are used exactly by two faces of the cell. What does it mean is that if you see the boxes, let's say there are sweet boxes, some sweet box you create by simply folding the sides. So each side is one face. So like you call it closed when all the sides properly connect to each other. So there you will see each edge is a part of two attaching faces. So that ensures that it is not open. The cell is closed. If edge is shared by more than two faces on one side and one face on another, then what we do that we create an additional point there at the meeting point and create, instead of one single edge, we create more edges so as to avoid this issue. Another is the orthogonality. Orthogonality is basically that two cells are, if there are two consecutive cells and you join them from center to center and you see the face, normal of the face. So angle between the normal of the face and the two lines connecting the center, their angle should not be more than 90. Because in that case, the flux from one cell to another would be 0. So that is the orthogonality. It's also part of the skewness. So we want to restrict the skewness to certain level. So now this leads to the another thing called as boundary. Once you have created the inner thing, you have matched the inner faces. Now you have to define at the outer, which defines the boundary. Outer. So there are list of patches in OpenFOAM. Okay, that is the name of the boundary, like inlet, outlet, wall. So like this, there are conditions which you do. So clearly one must contain only boundary faces and no internal faces. So boundary must be on the outer surface, not in the inside. And to ensure that all surfaces, external surfaces, have been patched with the boundary, the sum of all boundary face area vectors should equal to 0. So this condition ensures that you have not left any space which has not been given any boundary condition. Okay, so this is a mathematical way you ensure that all spaces are properly given the boundary condition. Now, when we have done this, so how the numberings are there in the OpenFOAM using the cell shapes. So you can see, we can take a hexahedron. Okay, so you can see in the leftmost, first we create a vertex 0. So this will be the origin. So 0. Then in the positive x1 direction or x direction, you create 1. So that is 1. Then in positive y direction or x2, you create 0.2. Then back to 0.3, which is in the negative x direction, but in the same, and then from 3, it will automatically come to 0 to create. And you see, if you see in this positive z direction, this is counterclockwise because the angle theta is positive in counterclockwise. Okay, and hence it will be able to create this face whose normal is in the positive direction, positive z direction. Now, to create this side, we defined 4, which is in the positive z direction, and from here again you follow the same sequence 5, 6, and 7. Once you are able to do, then it completes the hexahedron. Okay. Now, if you see, it creates 6 faces. So faces, you can see this is face 0, then 1, the front face is then 2, at the back face is 3, the bottom face is 4, and the top face is 5. And the edges, if you see, from this is the 0 edge, 1 edge, 2. So in this direction, 0, 1, 2, 3, then 4, 5, 6, 7, and 8, 9, 10, 11. So for x direction, keeping in the x direction, varying in the y and z, you are doing in the beginning, then keeping y common in variation in x, z, and then keeping z constant, you're doing in the other direction. So this is how you are having. So now you can actually visualize how the numbering is happening, why the sequence is important. Now you can create different type of geometries with the same. So for example, you merge 3 with 0. Okay. So you can create a wedge type. So what will be the thing? Basically here 0, 1, 2, and 0. So because 3 is now is merged as 0. And then this is the lower face, and the top face should be then 3, 4, 5, 6, because now there are only 7 points only. So you can easily understand based on this that the third point has now shifted to 0 location, and accordingly faces will be created. So this is how these are the faces, 5 faces. So 0, 1, 2, 3, 4, and 5. So these are the faces it will be creating. Okay, and accordingly edges are there. So if you want to create a prism, you can see here even the 6 has merged with 3. So what will you write? 0, 1, 2, 0, 3, 4, 5, 3. So this will create this one. So this is for the structure grid. If you want to go for, let's say, for pyramid, you know what to do. Okay, so tetrahedron and tetrahedron. So these are the different types it is creating and the idea behind that. So in the block mesh generation, as I said, the thing that is taken is that the point 0 is taken as the origin. Then the first point is in the positive x direction. The second point is in the positive y direction or x2. Then x3 and back. And then similarly for 4, 5, 6, 7. So you can see here that this edge 9 is curved, whereas the edge 10 is straight line. So normally it should have been a straight line, but you can actually make it arc type also. You can give what should be the curvature of this line. And the thing is, as I said, 3 points are always planar, coplanar, but the 4th point may not be coplanar. And here that is the case. It may happen that because of this, these 4 points may not remain coplanar, and hence the center of the cell of this face may not be physically on this area, but its projection in this direction would be on the cell face. Okay, so this is how mesh is generated. Now there is another thing that you might have seen in the previous sessions or will be coming in. What is the cell expansion ratio? Now, as defined, the cell expansion ratio is the delta T upon delta S. That means the last cell and the first cell. The ratio of that is the expansion. So if it is expanding, this will be more than 1. If it is contracting, it will be less than 1. So that's how it is defined. Now, if you look closely, basically what happens is the cells that are being created is following a geometric ratio series. So all of you must be knowing geometric series. So like if this first cell is the length A, then having a constant factor R, the next cell would be AR, and then next is AR square, and so on. So each consecutive cell would be having a ratio of R. So here you can see technically the expansion factor or ratio is last cell, which is AR to the power n minus 1 upon first cell, which is A. So this is the total expansion factor. So you can actually create on your own this, and you can write equation accordingly. Okay, and you can see that if R is more than 1, the cell will expand with consecutive cells. If R is less than 1, the consecutive cells will shorten. Now, why do we require this at all? That we will see in later part of the presentation. Now, next come, once you have created mesh, then you have actually create several blocks. Okay, so you may require to create several blocks, not just one block. Now, what to do? When you create multiple blocks, then there are issues. Like in this case, you can see these these are inner faces, whereas these outer, what you can see is the boundary faces. Now, if you are bringing them together, then you need to match the face. So when you are matching the face, they are formed from the same set of vertices. Okay, and the faces do not form an external boundary, and combine each collocated pair into a single internal face that connects cells from the two blocks. So you can merge two blocks, you can create them separately and then merge. What happens is that sometimes when you are generating geometry, so you generate different blocks separately, but then you bring them together and merge them into a single block. So when you want to merge them, you make a single block, you need to match faces exactly, because if they are not matching, the information passed through them will not be similar. So that is the requirement. Now another thing that may require is the face merging. Like in this case, so what happens here is a group of faces from one patch from the one block are connected to another to form the patch. Okay, and they to create a new set of internal faces connecting the two blocks. Okay, so now here when you merge these two faces, what happens? This external boundary is the new face rather than this and this together separately. So you can merge the faces when you have several faces which have the same, let's say, same boundary conditions. So let's say you have a cylinder and outer surface is the four different surfaces are there. Each of them is, let's say, wall boundary condition. So instead of working on them independently, you can merge them together and create a single boundary. So like this, you can merge the faces. So as I said, you can create a wedge or another type of mesh depending on the requirement from 8. So 8 vertices is the common, and what you can do here is 0, 1, 2, 3 in the first case, and to make this wedge type 4, 5, then 6 is written as 5 and 7 is written as 4. So 4, 5, 5, 4. So that will create this type. So whatever the type you need or it requires to be generated, it can be done accordingly. So actually there are several softwares are there now, commercial software and others are there, which actually are doing all these jobs on their own to make it more user friendly. But at the end of the day, at the back end, procedure remains same. Okay, they are charging you because they are doing on your part, making your life easy. And in those cases where this is not the case, you can do on your own and they are free of cost. So it naturally brings all these things together to us, is that okay, we have seen so many different types of meshing, so different types of the things. So what is the purpose of all together? And how will you decide which mesh to choose in what case, and what should be the number? So first of all is to have the adequate number and type of meshing. That is the very basic reason that why we have so many different types, because both the number and the type, okay, as Professor Harikrishnan has discussed structured, unstructured grid. In structured grid, there are different types we have seen. In an unstructured grid, tetrahedron, prisma, and other types of grid. So we need to have an adequate number. And why do we have that thing? First, to cover the geometry, because we want to cover our geometry properly. Okay. Second is to get the coherent and conservative numerical solution. Okay. Because mesh is nothing but the spatial representation of the basic equation we are using, the differential equation. So if you remember, differential equation is nothing but when we say d delta by delta x tends to 0. Okay, in reality, delta x never tends to 0. There is a limitation. So that limitation, that delta x is finite, is the visual representation in the form of mesh. Okay, so as mesh tends to be smaller, technically we are saying delta x tends to be smaller and approaching the differential equation. Okay, so as we are approaching that, we will get the result similar to the differential equation. And third is to simulate different types of physical phenomena which may require the different type of meshing. We'll see, and a later session will be covering that. So let's see this case. So now you see this is the surface we want to generate the meshing. Now, if the meshing, as previous session we have discussed, if the geometry is simple, and when I use the word simple, it means generally straight lines which are orthogonal. The structure meshing is straightforward case. No issue with that. So we are not interested in going for another type. But unfortunately, all geometries are not simple geometry. Like this is there. You can see straight lines are there, but some angles are there. Then there are curvatures. So would we be able to cover it with the structure meshing? So let's start with this. In this case, so snappy mesh is the thing which is going to generate. So let's say start with this. You can see now when we have a structure grid, then to cover this, we start the grid, the cells, small cell, larger cell, and all that. We start trying to cover every part of the geometry. So for doing the procedure, we create more and more to cover the boundary. So we need to do, so we created small cell somewhere, larger cell. So very basic idea is that wherever the curvature or the gradient is large, you require smaller meshing. Okay, the mathematical part is the Taylor series. When because we truncate it to the two terms, making it the first order. So the idea is that this delta x is small, but when the gradient is very large, then you need to make delta x even smaller further to make this approximation valid. Similarly here, so you can see when you remove the remaining mesh which is not required to be computed, it leaves the structure like this. You can see clearly that using this mesh, this type of structured mesh, we are not able to cover the geometry in proper way. The curvature is not taken up properly in this direction. Somewhere it is outer side, somewhere it is inside. So how would you cover it further? Then you further restrict the area which you require meshing, and then we further refine and change the thing, truncate this part. So you can see now those portions to cover or map the geometry boundaries properly. From this, it has been changed. So some portions are being removed in the sense those vertices are moved to the point. So different meshing is generated. Okay, this is why you require different type of meshing. Then to further capture certain places where, let's say here the drag is more or you want to see variations are high, so you create additional surfaces, additional meshing here. Okay, so another example can be taken, which I have taken from this reference. So you can see that wherever curvature is there, uniform meshing, structured meshing is not a very good idea because it does not cover curvature properly. So here you can see, here we have used unstructured grid, tetrahedron, okay, which is much easier to cover geometry, the curvature easily. Now, one of the important things that you can visualize here is, there seems to be solid sphere and cylinder, but what are the things you can simulate through them? So, depending on what is the properties of individual blocks, so they are different blocks, okay? We have made them different blocks, okay? From this, we have removed this portion from this, and this is there. So, their interaction is at the surfaces where they need to match. So, depending on the properties inside each block, you can simulate different things in the same geometry. For example, let's say I define air inside this block, and there is a liquid inside this block. So it's a physical case that bubble is in a liquid, and if I simulate gravity, then because of buoyancy, it should rise up. Okay. If there is no gravity, I'm basically simulating the zero gravity condition. Accordingly, you will see the effect. Okay. In the same, if I make the reverse, for example, in the same sphere, if I simulate, if I declare the property of liquid and this channel or this cylinder, I declare it as a air. So this will simulate the condition of drop falling in the air in a channel. Okay. So that is how I can simulate different things. I can simulate, well, let's say this is oil, this is water. So it's like a oil drop in the water. So same geometry can do several things. It can be considered static also. If this is a metal and this is another metal, I can see if in a heat transfer, how will they move, how will they expand or shrink. So just because certain geometry is there does not mean that by default the machine or the system will know that what to do with it. We have to define, and accordingly it will be work out. Okay. So if we have to create a cavity here, we don't have to give anything. We don't have to specify here. So that will be taken as there is no material inside it. So we can simulate a cavity also in the same place. So as we see, one of the reasons that different type of geometries, another numerical solution. So in numerical solution, one portion that has been covered earlier is the grid independence test. Now, why do you require grid independence test? Already covered by Professor Harikishni. Now, the important outcome of that grid independence test is the increased number of meshing, because you need to have a certain number of meshing at certain places. Certain place means those areas where you expect the variation gradients to be higher. So you need to capture them. So when you do that, the overall number of meshing may increase. Now, what it do is that it increases your computational time and resources. Okay, now the thing is you cannot avoid grid independence test to get a correct answer. If somebody thinks that I want to reduce the computational time and resource, so let me do it at a lower grid, it won't help. There are better ways, more intelligent or ways to achieve in a lower. So if you are using a direct solver, just giving you idea how much it is increasing. So like say in case of the structure grid, they are direct solvers we are using. Let's say if we are using direct solver, then the theory says that in one direction, it depends on the n cube. That means if you increase the number by twice, the computational time will increase by 2 to the power 3, that is 8 times. So if you are increasing the number in each direction by twice, that means you are increasing number of mesh by 8 times. The overall time will increase by 24 times. 8 into, so 8 into 8 times, which is 64 times. So you can see that one thing which you were able to do, let's say in 1 hour earlier, now it will take 64 hours to complete. So that's a very substantial increase. So we cannot choose the mesh blindly. We have to be careful while we cannot bypass this thing. So we can use structured grid, we can use unstructured grid, or a better thing can be a hybrid mesh if the software allows, which is basically a combination of structured and unstructured grid. Okay. So when we use hybrid grid, we can be more judiciously place more meshing around the place where gradients are supposed to be high. If we know beforehand or we expect from our understanding that in certain flow condition at these locations, the high gradient means high variation of, let's say, velocity, pressure, or any variable we are looking at is will be high. And we can avoid, we can provide coarse meshing at place where the variation is smaller. We can also use the symmetry for a given condition to reduce the total number of mesh. We'll see how. So let's say a simple case from this reference. So previously, before that, when it was generated automatically, it shows the nodes are 1400 and elements are 1309. So nodes are the points, vertex, elements are the cells. So we see these are the cells. Now when we make it properly arranged, let's say in a structured form here, whereas on these points we make it increased. So although this will give a better result than this, and with a lesser number of nodes, which is 1073, and elements are reduced to 982. So we can see the substantial reduction in the computational resources and time despite getting and besides getting a better result by judiciously putting the meshing. We can also see that the same geometry can be meshed with the different types. So you can easily see in one or the other condition, meshing numbers can be much greater. Like in this case, much less, whereas here it is much high in these cases. So while you will get the same result, but the computational time may be too high. Okay, so that is the thing. Another thing is like this geometry. This is a circular or the curvature geometries are always tricky one, because using structured grid we definitely like to do, but then you will not be able to capture the curvature easily in the structured grid. Here what you are seeing is the geometry visualization, but from the grid perspective it is very coarse. So if you want to capture the curvature well, the number of structure grid in the axial direction would be too high. On the other hand, the same thing can be easily achieved using the unstructured grid in a less number of meshing. So one of the tricky part is that which one to use depends on the post-processing part of the software you are using. Sometimes certain capabilities are applicable only to one type of meshing. So let's say there is one software, let's say you want to track the particle from the theoretical particle from entry to exit. It may be available only for structure grid. So if you want to do this thing that okay, how the particle is moving after the simulation, if the software does not allow for unstructured grid, you have to do it for structure grid only. So one has to see what gridding is that, what post processing is required, and based on that you can make a judicious choice. Another example from the console you can see is here. This is the rim of the tire, right? Now you can see while using unstructured grid, the number of mesh would be too high, whereas using hybrid, some places where the curvatures are high, you use the unstructured grid. Where the curvature is less and the variation expected to be less, we use coarse grid. So the overall number of mesh is much reduced. We can further reduce the meshing by exploiting the symmetry. So you can see it is symmetric in this direction. So if the force or the thing we are looking at is a uniform throughout, does not affect the direction, then we can take 1/5 of this and we can apply symmetry boundary condition on both sides. Okay. In case of turbine and such rotary dynamic, we can apply cyclic boundary condition, knowing that one outlet of one side becomes the inlet for the another. But if in this case the process is not symmetric, let's say there is a force on this direction only, then we cannot apply or use the symmetry of this thing. So we have to be careful while exploiting the symmetry. Another thing is like in this case. So here you can see there are two things. So it's a microfluidic channel inside a slab. So first of all, how do you know which is inlet and outlet? So you have to define boundary condition at this or this point. Second, by itself, the system does not know that which one is where the fluid should flow and where it should not. So you can see it that this is a glass tube in a pool of liquid, or you can see it another way that this is solid and the fluid is flowing in this one. So depending on the type of boundary condition and block properties, you can simulate different conditions. So there are two different colors because these two they represent two different blocks. And you can see if you more that since two blocks are connecting to each other, touching each other, their phase must match. Okay, then only you will be able to simulate, say, transfer of heat from one block to another or any other thing which we are planning to simulate easily. So that brings the another last slide, which is, so there are different types like in the triangular or tetrahedron or even a polygon type. This may be quadrilateral hexagonal type, and we can use hybrid in one direction and unstructured in another. So here you can see an example where different type of meshing is used in. So one structure is structured here, tetrahedral here. Okay, here you are making it even finer meshing using tetrahedral. Whereas on the other side, in this one, same geometry is meshed with the polyhedral and structure grid. So you can see and think of that in both the cases, number of meshing may be large in one, smaller in another. You may be able to cover geometry properly. Okay, the results, as you make any mesh smaller and smaller, you will get the same result. But at the end of the day, what is important is that you are able to get the results in a reasonable time with the reasonable effort available to you. You cannot plan that, okay, I have infinite time, infinite resource, I will be able to deliver. These are the practical constraints that leads to a limited choices. So that's all from my side. Thank you very much.
So if anybody wants to ask some questions to Professor Garg, you can go ahead.
Sir, for an airfoil case, which type of mesh would you recommend?
Well, I'm not expert with the airfoil type, but anyway, the thing is, as I said, depending on what is the level, what are the things you are looking for, is simply flow, what level you need to see. It may be different at different location where you expect more variation. So if the flow is less, the Reynolds number is less, the meshing may be more like this one, as you can see in this one. At the back, as the flow number increases, you at the back also you may require more and more finer meshing. So it depends what capability of the software your software is having. It also depends the computational power you have. It also depends the time you have to solve the problem. So in last session, previous session, Professor Harikrishnan said that in structural grid, it may be slower compared to unstructured grid. So let's say time is not the constraint. So you will see the computational power. In the case of unstructured grid, generally they are indirect solver which are iterative in nature. So it has a much lesser computational requirement. They are in iterative, so they take longer time, but they can do in a lesser way. Okay, so it all depends. It will ultimately bring down to that what are the constraints you are working in. So that is how it is to be selected. I hope I am not expert in that, but I try to answer to some extent.
Okay, sir. Thank you. Thanks a lot.
Hello, sir.
Yeah.
Sir, how can I initialize different kind of message in OpenFOAM? Today, I have initialized block mesh or hex type mesh in OpenFOAM, but in you are visualizing hybrid mesh and polyhedral mesh. How can I initialize in OpenFOAM?
I think there may be a separate session for that, Payal. If there would be a session for that, Payal?
Hello, yes, sir.
Yeah, so would there be a separate session to teach them the unstructured grid and the hybrid meshing in this course?
No, sir.
No, sir. There would be one for the unstructured grid.
Yeah, so I would suggest please be in contact with the FOSI team, and they may be able to help you guide in this how to do it. Actually, my purpose of my talk was to make you aware more about that these things can be done, and not as to how to do it exactly. So for greater detail, I would suggest anyone who is thinking of using hybrid grid, another thing, I think they better be in contact with the FOSI team, and they would be happy to help you out.
So if you want to use unstructured grid, what you can do is you can use Salome or make a mesh in ANSYS. Then you can import in OpenFOAM. That you can do.
Okay, sir.
Hello.
Yeah.
Hello, sir. Sir, this is Roshan from Roshan. So, sir, I am asking, sir, if I don't want to use any of the commercial software like ANSYS, then what is the possibility of generating this kind of polygon kind of mesh?
So if you are using any commercial software, what is
No,
this
no, sir, I don't want to use any commercial software,
Okay.
and I want to create this polygon kind of mesh.
Okay.
Then do we have some kind of some open software, or or using the OpenFOAM itself, can we how to create such kind of mesh, polygon mesh?
Okay, Anshuman, can you answer for that actually?
There's Blender. You can use Blender to create meshes.
Yeah, you
It's an
can
open.
use Blender, but we prefer Salome. Salome is a free open source software that we use time and again to create unstructured mesh and then
Okay.
import it in OpenFOAM.
Okay. Okay.
Sorry, what is it called? Salome? How do you
Yes,
spell
Salome. Salome.
it? Salome. Okay, thanks.
So can you explain the mesh for heat transfer from the surface which you have explained? So let me see. Second last slide is this one. I think this is what you're talking. So in this, if you are heat transfer, you're talking in this portion. I think, see, you can simulate several things depending what you are planning to simulate. So let's say this is a channel and the liquid is flowing here. So in this block, the blue one, you are defining the properties of a liquid. Okay. Now in this liquid, this is in contact with, so the green one is to be defined as the solid. So you will define is the property of solid. Now what solid? Let's say copper, glass, whatever that you want to say. So basically we are now saying we are trying to say that in this liquid, one side the liquid is entering, the liquid or let's say gas or any fluid, it is flowing through it and exiting at the other end. And while flowing through, it is interacting with the solid structure, the green one. Now, what are the things you can simulate? So you can simulate simply flow. You can simulate the heat transfer. You can simulate both at the same time. So like this, whatever you want to do. So the boundary condition will be accordingly. So for example, you want to simulate flow only. So the boundary condition for flow condition would be, so at the wall boundary condition. Now, if you want to simulate heat transfer also, then the boundary condition has to be there for the temperature. Now, whether it is the heat flux, whether it is a constant temperature, or you want to calculate based on convection, that you need to define. So if you define that boundary condition, it will take it as the heat transfer condition. And then you have to define then what is the initial temperature, what is the temperature at the surface or the flux. Accordingly, things will evolve. Now you want to couple it, then based on heat transfer, let's say the temperature inside the fluid is increasing. So if you do not simulate the changing in density and viscosity of the fluid along with the temperature rise or decrease, whatever the case may be, then you are basically decoupling the heat transfer with the momentum transfer, which may not give you proper result. Or under the condition, it may be acceptable that the rise or change in the temperature may not have a significant impact. There, in such cases, you can use it and you may still get a reasonable correct answer. But in the cases where viscosity, density is changing, are sensitive to temperature, there you need to model them as a variable of temperature. Accordingly, it will evolve with temperature, and accordingly flow and heat transfer will there, and that's where you can. So it will become a coupled problem, heat transfer and momentum transfer, and it will consume more time despite having the same number of mesh and everything, but it will consume more time to evolve into rightful solution. So I hope that is clear, or if there is anything I can help.
Sir, can you, if you wanted to know how much time the liquid would spend inside this, could you do that?
So you want to know the time, basically it's the residence time. So basically what is the total volume of this structure divided by the average velocity. So that will give you the residence time, average residence time.
I
so
see,
one
okay.
thing is this, if you already know it, then it's fine. If you want to calculate, then you can do the experiment. Also, what is the RTD of this system? That would be then transient study of this one. Then it won't be a steady state.
So that would be a different solver then.
Solver would be different. That's what I said. Depending on the process you want to simulate, the solvers would be accordingly. But the meshing, here I'm concentrating on meshing. So meshing will remain similar. Only the thing what you want to simulate would be thing. If you want to see the evolution of solution with time, then you naturally have to use a transient solver.
Okay.
Anything else I may help? So I think if no more question is there, I will say thank you, everyone.
We thank you a lot, Professor Dheeraj. It was a very good, informative session.
Thank you very much, ma'am. Thank you. Thank you, everybody.